Students, in this lecture I'll start with module 2. First we'll discuss the transfer function. So, the cause and effect relationship existing between input and output means to decide the transfer function of the given system is the mathematical indication of cause and effect relationship. Then this is commonly used to characterize the input-output relationship of the system. This transfer function explains mathematical function of the parameters of system performing on the applied input in order to produce the required output. This Laplace transform plays an important role in making mathematical analysis easy. So this Laplace transform and its use in control system analysis will be discussed. Now we'll go for concept of transfer function. That when we have a system, in any system, first the system parameters are designed and their values are selected as per the requirement. Okay, as per the requirement, the input is selected next to see the performance of the desired system. So the performance of the system can be expressed in terms of its output as output equal to effect of system parameters on the selected input. Therefore we can write output is equal to input into effect of system parameter. Therefore effect of system parameters is equal to output by input. Now these system parameters effect have a role of system parameters in the performance of system, which can be expressed as ratio of output to input. Then mathematically such a function explaining the effect of system parameters on input to produce output is called transfer function. Okay, because of the own characteristics of the system parameters, the input gets transferred into output once applied to the system. So this is a concept of transfer function. Now we'll go for the definition of the transfer function. The transfer function of a linear time invariant system is defined to be the ratio of Laplace transform of output variable to Laplace transform of the input variable under the assumption that all initial conditions are 0. Okay, we'll take the example mass spring dashpot system, and the dynamics is described by the second order differential equation, which is given as equation 2.1. Okay, then we'll take the Laplace transform of each term of that equation 2.1. Assuming 0 initial condition, we obtain f of s is equal to ms square x of s plus f of s x of s plus k x of s. Then the transfer function is g of s, which we can write it as x of s by f of s, which is 1 by ms square plus fs plus k. How to find the order of the system is whatever is the highest power of the complex variable s in the denominator of the transfer function determines the order of the system. For example, the mass spring dashpot system under consideration is thus a second order system. Okay. So the highest power of the complex variable s in the denominator of the transfer function determines the order of the system. For example, the mass spring dashpot system under consideration is thus a second order system. So, is it clear? We'll take the mass spring dashpot system under consideration is a second order system which has already been determined. Okay. This has already been told. So you can see in this, the mass spring dashboard system, the highest power of S is 2. Due to that, the mass spring dashboard system, which under consideration, is thus a second order system. Okay, and we can also even recognize from its differential equation. Next, we have studied electrical circuits, and we have seen what is the equation of that electrical circuit. From equation 2.22 and 2.23, we can have the transfer function of the LRC circuits shown is similarly obtained by taking Laplace transform of equations 2.22 and 2.23 with zero initial condition. The resulting equations are S L I of S plus R I of S plus 1 by S I of S by C equal to E of S. So 1 by S I of S by C is equal to E naught E of S, which is nothing but E naught of S. Okay. So if E is assumed to be the input variable and E naught the output variable, then the transfer function of the system is E naught of S by E of S. So which will be equal to 1 divided by LC S square plus RC S plus 1. So you have to substitute E naught of S as 1 by S I of S by C. Then you have to substitute E of S as S L I of S plus R I of S plus 1 by S I of S by C. So E naught of S by E of S is 1 by LC S square plus RC S plus 1. Okay, plus 1. Is it clear? So what does this reveal is that the above equation, the transfer function is an expression in S domain relating the output and input of the linear time invariant system in terms of the system parameter, and it will be independent of the input. This transfer function describes the input output behavior of the system, and it does not give any information concerning the internal structure of the system. Okay, so after determining the transfer function of a physical system, then the transfer function, the system will be represented by a block. Whatever is the system will be represented by a block. This is a shorthand pictorial representation of the cause and effect relationship between input and output of the system. So the signal flowing into the block called input is input, and flowing out of it is called output, that too after being processed by the transfer function characterizing the block. Okay, that has been shown here, you can see. This diagram represents, you can see, the diagram has been shown which represents the block diagram of thermal system. Then you can see this is a block diagram of the thermal system. Then you can see inside the block is written the transfer function. Okay. Next, we'll see what is the procedure for deriving the transfer function. The following assumptions are made. The following assumptions are made in deriving transfer function of physical systems. So what are the assumptions made in deriving transfer function of physical system? 1. It is assumed that there is no loading. What does this mean is that no power is drawn at the output of the system. If the system has more than one non-loading elements in tandem, then the transfer function of each element can be determined independently, and the overall transfer function of the physical system is determined by multiplying the individual transfer function. So if there is a system which is consisting of elements which load each other, then the overall transfer function should be derived by basic analysis without regard to the individual transfer function. The second assumption is that the system should be approximated by a linear lumped constant parameters model by making suitable assumption. So we are going to illustrate the first one point. We are going to consider two identical RC circuits connected in cascade as shown. What does this cascade mean? Means the output from the first circuit is fed as input to the second, which has been shown here. Then the describing equations for this system are, so we'll have the describing equations 1 by C integration minus infinity to t I1 minus I2 dt plus R I1 is equal to EI. Similarly, 1 by C integration minus infinity to t I2 minus I1 dt plus R I2 is equal to minus 1 by C integration minus infinity to t I2 dt, which is minus E naught. Then taking the Laplace transform of the above equations, assuming zero initial condition, we obtain 1 by SC I1s minus I2s plus R I1s is equal to EI of S. 1 by SC I2s minus I1s plus R I2s is equal to minus 1 by SC I2s is equal to minus E naught S. The transfer function obtained by eliminating I1s and I2 of s from the above equation is E naught of s by Ei of s is equal to 1 by tau square s square plus 3 tau s plus 1, where tau is Rc. Tau is equal to Rc. Then the transfer function, when it is taken of individual RC circuits, of each of the individual RC circuit, it comes equal to 1 divided by 1 plus s tau. So it is seen that the overall transfer function of the two RC circuits connected in cascade is not equal to 1 divided by 1 plus 2s into 1 divided by 1 plus 2s, but rather instead it is 1 divided by tau square s square plus 3 tau s plus 1. Okay, so we can see this. Is it clear? So this difference is explained by the fact that while deriving the transfer function of a single RC circuit, it is assumed that the output is unloaded. Is it clear? So if the input of second circuit is obtained from output of first, then a certain amount of energy is drawn from the first circuit and hence its original transfer function is no longer valid. The degree to which the overall transfer function is modified from the product of individual transfer functions depends upon the amount of loading. Okay? Is it clear? Now we'll take a problem. Derive the transfer function of this circuit given. Derive the transfer function. So resistor is in series, capacitor, output V0 of t, Vi of s, current flowing is Z. So we'll write first Vi of t. What is Vi of t? Ri of t plus V0 of t, because voltage across this capacitor is V0 of t. So Ri of t plus V0 of t, and V0 of t is equal to 1 by C. V0 of t is equal to 1 by C integration I dt. So I can write Vi, will take the Laplace transform. Vi of s is equal to Ri of s plus V0 of s, and V0 of s is equal to 1 by Sc I of s. I of s. Okay. So what is I of s? I of s we can write it as Sc V0 of s. So from this you can write I of s as Sc V0 of s. So Vi of s will become equal to sRc V0 of s plus V0 of s. So take V0 of s common, what remains 1 plus sRc. So Vi of s is V0 of s 1 plus sRc. V0 of s by Vi of s will become equal to 1 divided by 1 plus sRc, which is equal to 1 divided by 1 plus st. Okay. Is it clear? So I'll stop here in the where t is equal to Rc. T is equal to Rc. So I'll stop here. In the next lecture I'll continue the problems. You go through this, and in next lecture I'll continue with problems.